Welcome at the PSA webinar number 8. I'm David Raimon, hosting this out of Prague, Czech Republic, and the speaker today is Alexey Milkov, sitting in Denver, Colorado. Alexey will be talking on revised gas classification diagrams based on a couple orders of magnitude more samples than the original definitions of these diagrams. And I thought this was pretty significant contribution that people should be aware of. So I invited Alexey to give us a presentation on this. Alexey is currently a full professor at Colorado School of Mines and also a director of Potential Gas Agency at that school. And previously he worked at several oil companies, Murphy, Sasol, BP, and also at Woods Hole and Texas A&M as a postdoc. And he started in Vniakana Geologia. And he got his education at the St. Petersburg State University and Texas A&M University. Before we start, I want to thank Bill Dixon for supporting this webinar and helping cover the cost of this. In case of someone else, if you are interested in helping out with a little bit of money, just let me know or spread the news around your company so we can keep going with these presentations. And I think, Alexey, now you can start.
Okay, very good. So we're going to start, and if you have any questions at any point, I think you can ask me as we go along. I'm going to talk about revised gas genetic diagrams, and David mentioned that it's a very large data set and a lot of statistics. I'll focus less on statistics and more on kind of the application and results, and how the new genetic diagrams look like and what's different and what's new about them. And this work was done in collaboration with Giuseppe Etiope from Italy. So he's a co-author of the paper. The paper has been published, so I'll give you a reference later on. But I'll tell you more about why we decided to do that and to do this revision and how we actually went about making the decision. So now you see the outline of my presentation, and like I said, the first part will be on the motivation, right? Why did we think we need revisions, and what motivated us to do this research? Then I'll talk about how we did it, and that's where that large data set comes into the play, because we collected a very, very large data set, essentially from open data. And then we use this data set to revise gas genetic diagrams. So we focused on just on three most commonly used diagrams. So isotopic composition of carbon, isotopic composition of methane versus dryness. We know that as a Bernard plot, carbon isotopic composition of methane and hydrogen in methane. So it's a Whiticar plot or Schoell plot, depending on how you do it. And there is also a plot of carbon isotopes in methane and in CO2, which is used less frequently, but I personally find it very useful. So we'll talk about this one too. Right. So most of you, I'm sure, familiar with these diagrams. So, but let me quickly introduce you to these diagrams one more time. So this one is isotopic composition of carbon in methane versus the dryness of the gas. Right. So let me have my laser pointer. All right. So this is the dryness of the gas being expressed as methane over the sum of ethane and propane. And this is carbon isotopic composition of methane. So it was initially proposed by Bernie Bernard back in the 70s, and I'll show you the evolution of these diagrams. But what you look now is kind of the most commonly used diagram, the most commonly presented and published diagram. This one is from a recent presentation, recent publication, and that's how most people actually use it these days. And using this diagram, we can distinguish bacterial gas or microbial gas versus thermogenic gas. We also can think about the processes like oxidation and migration. You can also see these different kerogen types, type 2 and type 3, the arms for kerogen types. So we'll talk about that, where exactly they came from and if they're real or not. So the second diagram that we're going to be talking about is this plot of isotopic composition of hydrogen and carbon in methane. And again, the original idea was from Martin Schoell and Mike Whiticar back in the 80s. But what I'm displaying for you is something that we most commonly see in current publications, like in this one from Passion, right? So we have now the fields of microbial gas divided into two different pathways. So this one is microbial gas from CO2 reduction or bacterial gas, and this one is bacterial gas from methyl type fermentation. We also can distinguish thermogenic gas on this diagram and maybe think in terms of a relative maturity of methane. So we see this plot quite often. And the next plot is carbon isotopes in CO2 and in methane. So originally this plot came actually from Gutsala and Plotnikov, but it was published in Russian, so it wasn't picked up very well. Katarba was probably one of the few people who kind of promoted that in Western publications. So we'll talk about that a little bit more. But again, we can distinguish microbial gas, we can distinguish thermogenic gas, and in this case also abiotic gas, or what they called endogenic gas, and some different processes like biodegradation or oxidation. So all these plots are empirical, right? They're basically data behind them, and all the genetic fields are outlined based on interpretation of the gas samples. So what happens now is that when people have some gas data, they basically plot this gas data on one plot or two or three plots, depending on how much data they have, and interpret the origin of the gases they have, trusting that the genetic fields defined before are valid, right? So that's how we do gas interpretation. So what might be a problem with that, and why we may need the revision? We are now looking at a slide where I'm displaying the number of gas samples published each year, starting from 1960s and to present day. As you can see, the genetic gas diagrams were published, presented essentially back in 70s, in 80s, and the number of samples available at that time was in about first thousands, right? And right now we have so much more data because people publish a lot of gas data, and about 87% of all geochemical data on gases currently available came into open literature after the publication of these genetic diagrams. But we still use these genetic diagrams. We try to modify them, different people try to modify them, right? But it wasn't all encompassing effort. It was kind of ad hoc for specific reasons and for specific problems. So Giuseppe and I basically were thinking about it's time to revise these genetic diagrams. So before I show you what we did with the revision, let's get back to the evolution of genetic diagrams. And if you go back to the original papers, you can see how these diagrams actually change through time. So on the left right now, you see the genetic diagram, what we call now Bernard plot. So that's isotopic composition of carbon isotopic composition of methane versus the dryness of the gas, right? And that's how Bernie Bernard originally started this work. So he had some gases, right, from the Gulf of Mexico, 18 samples. So if you count, there are 18 samples on this plot. And some of these vent gases were coming from oil seeps, and he noticed that he and his co-authors at XNM noticed that this gas is relatively enriched in heavy hydrocarbons, ethanes and propane. and relatively enriched also in heavy isotope for methane in C13. So he basically outlined these 4 samples, right, and called petrogenic gas, now we call thermogenic gas now, and did the same for this group of gases, which were mostly methane and relatively enriched in light carbon isotope C12 for methane, and called biogenic gas. So that was the original Bernard plot. After that, basically in a 1 year time, he published another iteration of this plot. Now he added some samples from DCTP, but the original data set, I think, was the same as on the plot to the left. And now you see configuration of the fields a little bit more general, right, and kind of more reminding us, more resembling what we see now. But you still notice that the scale for carbon isotopic composition of methane is actually reversed, right? So we have -40 on this side and -80 on this side. And then in '88, there was a paper published in Organic Geochemistry by Faber and co-authors. And that's the first time when we see these arms of type 2,3 and type 3 kerogen displayed on the Bernard plot. The axis is now reversed, but the idea is exactly the same. What's interesting to note here is that actually, if you look at the samples behind that plot, right, we don't see samples within these arms. There's only 1 sample that kind of goes into, or maybe 3 samples that go into that type 3 kerogen, right? Still, we picked it up, right? People picked it up. And you see now iteration from Mike Whiticar in '99, and now this is very, very familiar, right? So as I showed you in the first plot, in the first slide, that's actually the diagram that most people currently use. So now you have this thermogenic field and microbial field, and you have 2 arms for thermogenic for different kerogen types. And also Mike Whiticar distinguished methyl type fermentation pathway from predominantly CO2 reduction pathway on this diagram, because he was mostly working with microbial gases. Some other people try to do other things with this diagram. So for example, in this paper by Harita and Bernd, they were working on abiotic gases. So they sampled gases from mid-ocean ridges, from ophiolite, I think, and ophiolites. And they started to plot these boxes of abiotic gas on this diagram. So it wasn't picked up very much, so we don't see many iterations of this diagram later on. So it was kind of, but importantly, they tried to put abiotic gases on the diagram. And back in 2011, I published a paper in Organic Geochemistry focusing on secondary microbial gas. That's gas from biodegradation of oil. And I was basically doing empirical identification of the genetic field for this secondary microbial gases. So I also tried to modify this diagram. But this modification by Harita and Bernd and myself, these are not universal, right? This is kind of to address specific issues. So now let's get to the second diagram. And the second diagram is isotopic composition of carbon and hydrogen in methane. And originally it was published by Martin Schoell in APG. And now we see, so this is carbon isotopic composition and this is hydrogen isotopic composition. And he was distinguishing gases of bacterial origin, continental and marine source rocks, and thermogenic gases. In the next iteration, there was a paper by Whiticar, and I think they worked very closely with each other. And in this case, we have just this kind of different scale, I think, and slightly different iteration. But we see samples that they actually used to define the fields, right? And then this iteration from '99 from my Whiticar, that's probably the most commonly used version of this diagram, right? So we see now thermogenic gases as early mature and associated and from humic, and we see some geothermal gases, abiotic gases, right? So there's more interpretation and information coming in. In my paper on secondary microbial gas, I try to define the field for that secondary microbial gas. Again, very empirical from the data set that I had before. And my co-author for this work, Giuseppe Etiopa, he spent a lot of time looking at abiotic gases, especially in the last 5-10 years. So he was, in his publication over here, he was trying to make some empirical genetic fields for different types of abiotic systems. Like this pink one is volcanic geothermal system. I think there are ophiolites and crystalline rock somewhere. So different people tried to modify this diagram, but again, it wasn't a universal effort. All right, and the third diagram we're going to talk about is carbon in methane and in CO2. And this one is the original plot from Gutsala and Plotnikov. So this is carbon isotopes, this is CO2 isotopes, and they define fields of biogenic methane, thermogenic methane, and abiotic methane. And you can see the samples that they actually used for that. It was published in Russia, so it wasn't picked up extensively in the Western world. But Katarba published this iteration basically with, I think, with reversed scales, right? So now he plots CO2 on this x-axis and methane on the y, but the fields are essentially taken from Gutsala and Plotnikov. And Mike Whiticar, he did work on microbial methane, right? And also used this CO2 and methane carbon isotopes to distinguish between carbonate reduction and methyl fermentation. And there was also this field of oxidation. And then I did the same for secondary microbial gas. And in this case, it was very important because secondary microbial gas has CO2 highly enriched in heavy isotopes, right? So CO2 actually is, an indicator of secondary microbial gas being present. So for me, that was very important to actually use that diagram. Right. So now we have all these original diagrams, and I discussed the evolution. So most important things about them, they are empirical, right? So they are based on samples that people kind of made judgments about the origin of the samples and then outline the fields around them. And then when new samples were available, if they fall in the same genetic field, then they have the same origin, right? So that's the first thing. Second thing is they all based on relatively small data sets, so tens to hundreds of samples. So if you think about, back to the original Bernard plot, right? So there was 18 samples from ships in the Gulf of Mexico and a few samples from the CDP, right? And now we have thousands and thousands of new samples. And when we plot these new samples, many of them actually plot outside of the originally defined genetic fields. Right. So, and when I saw that first time with my secondary microbial gases, right, so I basically decided to put that secondary microbial gas on all the diagrams, right? But maybe there are some other gases that also don't plot outside. So that's why we decided to actually go through that revision. And also we have these new types of gas origin. I already mentioned secondary microbial, but also early mature thermogenic gas. People have been talking about this early mature thermogenic gas for quite some time, and occasionally recognizing it, but it hasn't been formalized properly. So we try to do that. And also for abiotic gases, especially for Giuseppe, because he works on abiotic gases quite a lot, right? We wanted to have abiotic gases on all diagrams, because gases do have that origin. Some gases do have that origin. So how did we do our revisions? What was our methodology? First step was to assemble that global data set of gas samples. And we did that by looking at published papers and reports, right? So with new papers, all the tables are digital, right? So it's easy to copy and paste. With all the papers, we had to retype a lot of gas information, a lot of gas data. And then some governments have data sets and databases in the open with data. So USGS is very good about that. Australia is fantastic. UK recently released a huge amount of data on gases from the North Sea. Norway has a data set which with drilling data, and you can go into specific fluid reports and get the data. And also Netherlands, I think, has a nice database. So we put that information together, all this data together. And then we started interpreting individual samples, right? And that interpretation was holistic, It was geochemical and geological base. So we looked at gas composition, and then we also looked at geological habitat of the samples, right? So where exactly that sample sits. So for example, if we have gas from a hydrothermal system with no sediments, with no organic matter in the area, it's probably abiotic, right? If we have gas from a shallow section where there is no source rock, there is no maturity, and it's only methane, right? And it's very light isotopically. Methane is probably primary microbial gas. So we went and looked at each sample and basically assigned origin to these gas samples. And then we plotted samples on the diagrams and defined empirical boundaries of genetic fields. So essentially it's the same approach as was done with these diagrams before, right? There is no theoretical justification for these genetic fields to be where they are. These are empirical genetic fields. All right. So let me talk about the global data set that we have. So it's large, right? So in the paper, we used about 20,600 gas samples from 76 countries on all continents. Right now, the database, it's about 23,000 because the new data being published essentially every day, and I have Google alerts, and every time I see gas data, I enter that into the data set. On the map, you see the distribution of the samples, and on the right, you see the continents with the number of samples, and clearly Asia and North America dominate in the number of samples. Most samples coming from the US and from China. Huge data sets are available from China these days. All right. And this slide shows all the countries from which we have samples, and just zooming in on the top 10, you see that US and China, we have about the same number of samples, and they dominate the data set. Between them, two of them, more than half of samples are actually in these two countries. But we also have samples, a lot of samples from Russia, Canada, Australia, and so on and so forth. Right. The habitats of samples. Most samples come from petroleum reservoirs. The database is very much biased towards petroleum reservoirs. That's where most data are available, and that's where my personal interest is as a petroleum geologist and petroleum geochemist. But among these petroleum reservoirs, we have conventional reservoirs, about 14,000 samples, and we have also large data sets now for coal beds and for shale reservoirs. And shale reservoirs is especially interesting because there's a lot of information on shale gas coming out. And you see also some other habitats like serpentinization and lake sediments and freshwater sediments. There are not many of these samples, but they're actually very useful because they help to define some specific fields like abiotic gases, for example, or different processes like oxidation. Right, the depths of gas samples, most samples are relatively shallow. So if you look at the depths, you see that about 1,500 of samples are actually at the surface. So these are the seeps, these are vents, maybe surface gas hydrates, things like that, mud volcanoes, right, bubbles from mud volcanoes. And then with depths, we have a decreasing number of samples, which is expected. And the deepest samples come from Sichuan Basin and Tarim Basin in China, right? We have some samples all the way to about, I think, 8,600 meters from Tarim. You don't see them on this plot because the number is small. These are just few samples, 2 or 3 or 4 samples. So that's why you don't even see them on the plot, but they're there. All right, so composition. Before we move to genetic fields, let's see what kind of gases we actually have. So on the left, you see a plot of hydrocarbons, CO2, and nitrogen. And the way I'm displaying it, I'm basically plotting the ratio of CO2 in the sum of hydrocarbons and CO2 versus the same for nitrogen. So nitrogen in the sum of hydrocarbons and nitrogen. Essentially, when it's 0 for both CO2 and nitrogen, right, we have pure hydrocarbons. This would be a pure nitrogen, this would be pure CO2, and this would be no hydrocarbons. So right away you can see that most of our samples are actually heavily enriched in hydrocarbons, right, and don't have that much CO2 or nitrogen. But we have a variety, right? There are some conventional reservoirs, and conventional reservoirs here are in red. There are some conventional reservoirs with essentially no hydrocarbons, right? So this is just gas of CO2 and nitrogen. And I'm focusing on the red dots because these are conventional petroleum reservoirs, but you see some other dots on this plot, they come from other habitats. So that's another data set to mine for the future. And if you look at all the gases, methane is a dominant hydrocarbon gas, which is completely expected, right? So most samples have, high amount of methane, but not all of them, right? In some samples, we do have high concentration of CO2, of heavy hydrocarbons, ethane, propane, butane, and pentane. So these are some statistics on parameters that actually went into our genetic diagrams. So the first plot shows dryness, so the ratio of methane to the sum of ethane and propane. Second plot is carbon isotopic composition of methane. This is hydrogen isotopic composition of methane, and this is carbon of CO2. So you see the number of samples, right? And the numbers are all different. And the reason for that is that not all samples have all information available for them, right? So for example, not all gases have isotopic composition of CO2, carbon isotopic composition of CO2 measured for them. So we have only 6,000 samples or so, right? Another thing to note is that we are presenting minimum and maximum values, right, for all these parameters, but we're actually not presenting the mean. And the reason for that is that the mean or the average values would be actually quite meaningless because most samples come from the US and from China. So whatever average values are basically just representative of these two countries and the basins in them. So we don't have a global average gas composition. So we didn't want to mislead people in regards to that. Because this is just samples, right? Just published samples. All right. So back to our revisions, right? So I mentioned that one of the reasons was to revise. Was because samples plot outside of the originally defined fields, many samples. And here's an example. So we are looking again at this Bernard plot diagram. So carbon isotopic composition of methane versus dryness, and these are original fields defined by Bernard and now used in many papers, right? So this is thermogenic gas, and this is microbial gas or bacterial gas. And now you see many samples that we have in our data set that actually don't fit into these fields, right? So interpreting them becomes, some kind of a stretch. All right. So another thing that we noticed was that when we separated our shale samples and coal methane, coal seam gas samples and plotted them on Bernard plot, right? There wasn't actually much, there was a huge spread of the data, right? Data did not conform to this type 2, type 3 kerogen, so type 2 being essentially marine shale and type 3 being essentially coal. So CBM gases, right, which are kind of orange dots here, right? They're all over the map, right? So all over this plot. They don't just go into this one. Obviously, there are different origins of CBM too. But even for the shale gas, which is supposed to be, all type 2 marine shale, right? It's actually not necessarily the case. So, so that was another motivation for us to revise these diagrams. So how did we do it? As I said, we use a holistic approach. So we went for each sample, right, and identify the origin of that sample based on all geochemical information that we had available, plus geological information. And we were able to do it for about 6,000 samples that are plotted on this diagram. It's about 50% of all samples in the plot. So basically what I'm saying is that we assign some kind of end member or pure origin of the gas, right? And we color coded this in this diagram. We'll color coded the origin of the gas. So for example, this first violet color, right? These gases are abiotic, right? based on the geochemistry and based on the geological habitat. That was our best judgment for these samples. And these gases are microbial gases from CO2 reduction, and these black dots are secondary microbial gases, or gases with significant contribution of secondary microbial. But you see that many gases, actually, we don't have origin of these gases assigned, because we just couldn't figure out what it might be. It was potentially some kind of a mixture, as you can expect, for example, between microbial gas and thermogenic, right? Or it could be some kind of post-generation processes. Like these samples, they're probably oxidized. So we basically focused on samples that we could kind of reliably say, to the best of our ability and the best of our judgment, reliably say that they have this type of origin. So, and then we took that previous slide and basically outlined the fields, genetic fields on this diagram. So that's how our revised genetic diagram for carbon in methane and dryness now looks like. So you can see it's very different from the currently used versions of Bernard plot, but there are also lots of similarities, right? So most gases that we used to see in, right, primary microbial gas or thermogenic, they're still there. It's just the fields are slightly different. But we also have two new fields. So this is secondary microbial gas. So that's gas from petroleum biodegradation, and this is abiotic field, right? So now we have that. Also for thermogenic gas, we are distinguishing between early mature thermogenic gas, mid mature, or oil associated for lack of a better term, and late mature thermogenic gas. And for primary microbial gas, we have CO2 reduction and we have methyl type fermentation. This is essentially very much the same as it was defined originally in Whiticar's plot. Right. And then we also looked at different processes, and this the same diagram, but now I'm showing the processes that actually can affect different gases. So importantly for thermogenic gas, we think that's the maturation pathway, right? Here's a biodegradation pathway. So we start with this mid-mature oil associated gases, and they become drier, right? And they also end up with about minus 50 per mil on methane. We still have mixing and transition between thermogenic gas and microbial gas as in original diagrams. Here's the oxidation, here's thermochemical sulfate reduction and migration. So we looked at different samples and basically thought what kind of processes may affect these gases. Right. For some of you, this term secondary microbial gas may be new. So let me formally define what I mean by that. This is a diagram from my recent paper on secondary microbial gas. And essentially, what we call primary microbial gas or primary microbial methane is a gas generated from dispersed complex organic matter, right? So that's low TOC, usually tertiary sections, right? Usually low temperature. That primary microbial gas very much enriched in light isotope, dominated by methane, but there is some ethane and propane, we think, being generated in this process also. So that's your recent discoveries in Zor, for example, or in offshore Israel, or in Myanmar. So that's primary microbial gas. And secondary microbial gas is the gas that was generated by microbes during the biodegradation of oil. So we start with with source rocks, right? Then we have generation of oil, and then microbes eat that or consume this concentrated organic matter and generate predominantly methane. But we also think there are some other gases also being generated. The pathways are probably the same, so CO2 reduction is probably the dominant pathway, but there are some other pathway around methyl type fermentation and maybe methanol, consumption of methanol. So, but predominant is probably CO2 reduction. So that will be the secondary microbial gas. And I'm pointing this out because now it's on diagrams, so we better all understand what exactly it is. So another thing that is kind of unusual or new about our Bernard revision is that we define this early mature thermogenic gas, right? And as I mentioned before, people people talked about early mature thermogenic gas previously, right? So especially on occasion when they see them in shales, in Green River shales, for example, people were kind of seeing that, it's isotopically methane is very light, maybe minus 70 per mil, minus 75, but the processes are actually kind of thermogenic rather than microbial. So people started to think about that. Now we have more gas data from shales. And some of these shales that people drill through, they're actually not very, very mature, right? So, and when we sample these gases, we think we actually have this more concrete evidence of early mature thermogenic gases. So let me show you these three examples. These are all gases from the shale. This is Jurassic shale from Paris Basin in France, and these are two gas samples from the shales in Canada. And on the right, I'm showing the Chan plot. And in the Chan plot, if you believe the Chan model, right, we can plot carbon isotopic composition of different gas compounds, so methane, C2, C3, and C4, right, as a function of 1 over carbon number. And gas of one origin, right, from one source rock, one origin would plot on a straight line. Right, and as you can see, these gases do plot on approximately straight line. The concentrations obviously are small for C2, C4, right, as we can see from the dryness, but they were sufficient to measure isotopes. So they plot on the same line, and they also have propane, and they also have butane, right, in some cases. And propane is in insufficient concentration to actually say that it's probably not generated by microbes. So based on that idea of using Chan plot and basically saying that it's approximately the same, approximately straight line, and we have sufficient propane to measurement, these are probably thermogenic gases. And also looking at the geological setting of these gases, right? So these are shale gases, so they're basically inside the source rock, and they are at low maturities, right? So this is not in oil window, right? They kind of sit in, I forgot the exact temperatures, but maybe about 70, 90 degrees C. So this is what we decided to call early mature thermogenic gases. And there are not many of them, right? And I'm showing you the shales because that's kind of the most geologically reasonable, but you also have some accumulations of that gas, for example, in West Siberia. So hopefully we're going to see more of that early mature thermogenic gases as people actually think about the possibility of them being present, right? They generated in small amounts relative to mature thermogenic gas. That's why we don't see them in accumulations. We don't see them very often. But when we are inside the shale that is going through early mature thermogenic processes, that's a place to see it. And I think that's exactly what we have on this Chan plot. All right, so now let's talk about revision of hydrogen and carbon isotopes diagram. So again, same idea. Here's a plot with genetic fields from Mike Whiticar, and all these black open dots are our samples. And you can see how many samples actually plot outside of genetic fields that were defined originally. So that's exactly the reason for revision. Use the same process, so holistic geological, geochemical interpretation of each sample. Again, we interpreted about half of the samples available on this plot, and other gases are mixtures or may be affected by some kind of post-generation processes. So we only focused on the ones where we could reliably say that we understand the origin of this gas, or we think we know the origin of this gas. Right. So here's the revised diagram. So in this one, again, the new field is this secondary microbial gas, right? But also you see a lot of overlap for this early mature thermogenic gas and primary microbial gas from CO2 reduction and from methyl type fermentation. So and also secondary microbial gas in this case. So a lot of overlap is potentially possible, right? And I think people already struggled with that. And the best way to distinguish these gases, I actually use some other plots, right? But what's good about this one is that abiotic gases now have a very, very large distribution on this plot. I'll just go back and show you the original data. So these are all gases that we think are abiotic. So this plot is fantastic for distinguishing abiotic gases from biotic gases. And on this plot to the right, we show now different processes that affect gases. And again, you see the same things. You see maturity for thermogenic gases increasing, has a biodegradation, has a microbial thermogenic transition and mixing, oxidation, and TSR. So we can use these plots to do interpretation of different processes. All right, so the next diagram is carbon and carbon in methane and carbon in CO2. So again, same idea, right? We are looking at all our data in black dots, black open dots, and genetic fields from Schoell, Plotnikov, and Whiticar. And you can see that the data don't conform just to these genetic plots. So we need to revise. Use the same approach, use the same methodology, looked at each sample, assigned the origin, and plotted it back on the diagram. And this one is our revision. So what you see here is that we actually have quite a lot of overlap for isotopes, carbon isotopes in CO2 when the values are less than 0, right? So have a lot of overlap in these genetic fields. But what's important, especially for me, because I studied this secondary microbial gas quite a lot, right? We can actually use this diagram to very reliably identify the presence of secondary microbial gas from petroleum biodegradation. Essentially, when we have values more than +2, it's very likely to be secondary microbial. We actually found some primary microbial gases with values up to +15 on CO2, and we found some very, very late mature thermogenic gases with values up to +8. I think, right? But you can distinguish them based on carbon isotopic composition of methane, right? So that secondary microbial gas is quite well defined in this diagram. And again, I'm showing different processes that can affect gases in that space. So essentially, that's our revised diagrams. So my key messages, what I want you to remember is that we all use these empirical gas genetic diagrams, but these original versions are probably outdated and partially inadequate, right? Many samples plot outside of these defined fields, and which makes them partially inadequate. What we did with Giuseppe, we revised these 3 diagrams, and we used a global data set. It's from around the world. It's from different geological habitats, more than 20,000 samples. We placed all the normally recognized origins of the gas, thermogenic gas and primary microbial gas on these diagrams, but we also took care of secondary microbial gas and abiotic gas and put them on all 3 genetic diagrams in a consistent way. One thing to remember when we interpret natural gases is that gases are mixtures, right? I'm saying many, but I think most gases are mixtures depending on how you define mixtures. So that interpretation of gas data needs to be holistic. You have to use all available geochemical information, both molecular and isotopic parameters, and maybe also, definitely not non-hydrocarbon gases, maybe also noble gases, right? So you have to use all the geochemistry, but also geology. What's also the geological setting, right? What's the habitat? What is the fluid phase of the reservoir, and so on and so forth. So that's the key to reliable interpretation. Integrate geology and geochemistry. They have to be consistent. Right, so I gave you a brief overview. I think we spent about 45 minutes. But if you want to read more about these diagrams, the paper is published. We published it back in November in Organic Geochemistry. Here's a link, or you can just send me an email and I can give you a PDF file for this paper. Another thing that I want to mention is that we talked about gases, but I do more comprehensive class on petroleum fluids and source rocks in ENP projects. It's a 3-day course with a lot of exercises, and we go through whole value chain from exploration to environmental remediation. And I can teach this class in-house, or it's also publicly available through SCA. And what people like about this course is how practical it is. We do a lot of exercises, it's all applied, right? So people really like that they can take the knowledge and do stuff next day back in their workplace. Right, so I'm ready to take your questions and comments. But if you want to visit me, here's where I live now, right? So that's Colorado School of Mines, or you can just send me email. Here's my email, and I'll be happy to answer your questions. Thank you very much.
Thank you, Alexei. Are there any questions for Alexei now?
Yes, please, if I may.
Yeah, go ahead.
Thank you, Alexei, for your presentation. But there is a giant work have been done. So you've reviewed all these modular samples, but what's about the reviewing of the temperatures of the primary microbial gas generation, because there are also some overlaps and some controversial theories of what's the temperature range of the primary microbial gas generation. Is there any update or your maybe opinion on what are the ranges? Thank you.
Yeah, so I do watch the space, so I'm kind of watching what people think, and so where I stand, what my opinion on this is. So the maximum temperature for microbial gas, primary microbial gas generation, is probably about 80 and 90 degrees C, right? That's what most people think, and I think that's that still stands based on for example, on laboratory experiments. The optimal temperature is probably about 35, 45 degrees C. I think that's where we see that the peak of generation of primary microbial gas, again confirmed by laboratory experiments. Now, with microbial gas, what's important to remember is two things, right? First one is that it's the rates, and that's the amount of generated gas. So maybe we can have some primary microbial gas generation at high temperatures, let's say 100 degrees. The question is how much? That's one thing. Second thing is, when you think in terms of geology, right, we do see primary microbial gas at much higher temperatures, right? That's fine, but it's not necessarily that that gas actually forms there. That gas could actually form at early temperatures, and then during the burial, these accumulations could be buried down and to their temperature. So you have to separate, the temperature of microbial gas reservoirs versus the temperature where this microbial gas was generated. For this specific study, right, why we introduce early mature thermogenic gas rather than microbial gas. So it all goes back to propane and maybe butane and pentane. So as soon as you see butane and pentane, right, it's probably not primary microbial gas. You probably have thermogenic gas, right? If you don't see it, right, it's probably microbial gas. So that was one of our criteria, right? So we only used primary microbial gas identification or assignment for samples when we don't see any C4 or C5. As soon as we see C4, C5, for us it was an indication that actually it might be the thermogenic processes are going on. So, and that goes back to laboratory studies, right? So to my knowledge, there are no lab experiments where butane and pentane is produced by microbes. So I know of some minor propane, I know ethane, right, is microbes do that, right, but not C4, C5. So that's kind of, that was our logic, and that's where we stand.
Okay, thank you. But what's the, so in my imagination, so for example, we start to produce the microbial system start to produce gas at 30 degrees, but then the temperature, so that the temperature due to subsidence maybe increase, and the rate is maximum at 30, as you said, 35-45 degrees. But then my second question, so at what temperatures the microbial system starts to produce the gas, and if it is killed, can it be reborn, or if it's killed, so it's forever and so on?
Yeah, no, that's a good question, right? And that's why, in one of my slides, I mentioned the transition, right? Mixing and transition, right? So I don't think it's a switch, right? I don't think you go from, purely microbial to purely thermogenic. I think there is some kind of a transition. And if you think of shales, right? First, you have this primary microbial gas in the pore space, right? So you actually generate that, and then you kick in thermogenic process, and you start having addition of thermogenic gas, and it's all mixtures, right? But it's all in very small amounts to start with, also. So it's I don't think it's a switch, right? I think it's a transition, right? That's one thing. I think that microbes basically at temperatures, let's say 70, 80 degrees, right? They just become less important, while thermogenic processes start become more important, right? So there's some kind of a transition between these two, and the rates and the amounts, and that's what, and then we go completely into thermogenic, and we flush all this primary microbial gas in shales that was there originally by just abundance of thermogenic gas, right? And that's why we don't see it, later on. So so I don't think it's a switch. I think it's a transition. Now, but in my mind, this topic is very much understudied, right? So that primary microbial gas, we still use plots and ideas from Chris Clayton, right, back in 80s and early 90s, right? And there's not enough laboratory experiments going on this. And but now with the discoveries in Israel, right, or in Egypt, right, with Zohr and all these discoveries, or discoveries in Myanmar, it's a very hot topic, right? It's a very interesting topic. So I think we need to do more research in this area. I think we kind of understand, but it's very much mental picture and what's possible. We don't have very solid research to understand the transition from microbial to thermogenic.
Okay, thank you very much.
I see a question by Liz Chapman. Thank you for your presentation. Could you explain what you mean by the migration process on your revised genetic diagram?
Yeah, good. So so this one, let me see if I can actually get back to that. Right. So yeah. Right. So this one, so migration, right, on original Bernard plot, carbon isotopic composition of methane versus dryness. So this was a debate with Giuseppe for me personally. By migration, essentially what we mean here is that during the migration, right, we actually can have some fractionation of the gas, right, compositionally, but not isotopically. So isotopes of methane during migration probably don't change, but the gas composition during the migration may change. Essentially, gas during migration, right, can be more enriched in methane. And the argument for that comes from the SIPs, right? And there are very, very few cases when we can actually compare the subsurface accumulation and reliably connect it back to the SIP, right, and compare these two compositions. Now, my counter argument for this error is that when we actually have enrichment of methane during the migration, it may be not because methane is lighter and migrates faster, right, as would be migration effect. But maybe because there's biodegradation in shell section, so we actually remove C2 and C3 during biodegradation, and also because there's secondary microbial gas, we actually add methane to this one. So my understanding that in most SIPs, right, that we see at the surface, they are more enriched in methane because of biodegradation and addition of secondary microbial gas rather than because of migration effect. So Giuseppe's argument is that during the migration, C1 should migrate faster than other hydrocarbons because it's smaller and light. So, and we left this one because it was in the original plots. If you remember back to Whiticar 99, right? So that migration was kind of there. So we left it there. But to be honest, we had a debate about this, and yeah, I'll leave it at here. Yeah. So
I have a question. So when you look at each of these plots, you see a lot of overlap between those fields.
Mm-hmm. Yep.
And have you tried to look at the combination of these plots and see whether it can help you that you see certain sample falling into a couple or three different fields, and other plot helps you to distinguish in between? And yeah, any comment on that? Whether you've done some statistical analysis on this, whether it's actually helping you to fingerprint?
Yeah, so it's a great question, right? So yes, so we see a lot of overlap, right? So, and the answer to your question is, as soon as your samples plot in the areas of overlap, right, you have to use other data, right? So basically, just looking at isotopic composition of methane and dryness, right, and if you have a sample in this area, right, where a lot of things are actually overlapping, all right, so you basically cannot say what your sample is. You have to now use some other diagrams, and you also have to use your geological context. So let's go back to this area, right, where we have thermogenic gas, kind of mid-mature, and abiotic and secondary microbial, all potentially overlapping, right? There are lots of samples actually in this area, right? And also many people, when they see sample in this area, they interpret that as a mixture between primary microbial and thermogenic. Right, so there are basically four different ways to interpret gases in this area. So how do we know? So first thing is, okay, can it be secondary microbial? So that's where CO2 isotope, carbon isotope and CO2 becomes very useful, right? Because if it's +2, right, it probably would be secondary microbial. So you can use that diagram. Can it be abiotic? That's where hydrogen isotopes for methane become very useful, because on that diagram, abiotic gases actually take a special place. Right, so you have to use that second diagram, and of course you need to look at your setting. If your gas comes from biodegraded oil accumulation, right, in the shallow section, it probably has significant contribution of secondary microbial gas. So that's exactly the point, right? The diagrams are not as simple as they used to be, right? There's a lot of overlap in them because the gases, and when we look at a huge data set, right, the gases are all many of them are mixtures, right? There are different processes. So the world is not as simple as people thought about it back in the 80s. So that's why we see a lot of overlap in this diagram. Are they still useful? Of course they are still useful, right? We still can use them to define origin of gas, but we have to use more than one, right? We have to use at least these three, right? We also have to use other diagrams because, look, I didn't talk even about isotopic composition of ethane, right? Or I didn't talk about, you know, all the hydrogen isotopes in all different gases. I didn't talk about isotopes of nitrogen. I didn't talk about noble gas. So you have to use all that information, and you have to use geological setting, right? Only then you can have a reliable interpretation. So that's a very good question, and thank you very much for that, because my message for you guys is the world is more complex, right? Don't use just one diagram, use all of them, use other data, use geology, right? So that's the first part of my question. Now, the second part is, because you asked about statistics, right? So right now I'm showing you where we are currently, but the data set right now is about, I'm getting close to 1 million entries, right, on all different gases. So we started the project here at Mainz, where I have a student who is actually doing, big data analytics, machine learning, right? And we are trying to see what we can do with this data set and move, beyond these diagrams and maybe use this, multiple data and correlations that we're still trying to find what they're going to be, to give some kind of, first give an automatic interpretation for the gases, but also put some kind of a probability and confidence levels on this interpretation, right? So you basically take a sample, right? You put everything that is possible, and for that data set that you have, which is also not complete necessarily, right? You can say, okay, this sample is probably 90% thermogenic, right? 5% is possible that it's secondary microbial, and only 2% that it's abiotic, right? So, and that's going to be fast, right? And going to give you some interpretation guidelines, and obviously then you need to, as a person, as interpreter, as the person with experience, you need to look into that. So we're working on that, right? So we have that machine learning project running on this data set. And if you're in industry and if you want to support this project, definitely, write me an email, and we'll talk about that.
All right. And I see one more question by John Pantano. Can you comment on gas isotope ratios and wetness trends when the gas remigrates or accumulates because it comes out of the oil phase due to bubble point phase separation?
So it's a very specific question to some problems that you're working on, I guess. So I don't have a question. I don't have a comment on this because it's to me there's some general kind of global things and there's some specific cases, and this question to me it's kind of a specific case where we need to look into that possibility of gas fractionation during migration, right? But also I suspect there might be some other processes, some other explanation for that case. So for that type of question, I would prefer to actually look at the data, right, and complete data set of geology and geochemistry to explain why gases might be different. Is it migration or is it a mixing, right? Maybe there is another source rock working and contributing to accumulation, and maybe there is a microbial gas that was pre-existing before the oil accumulation moved into that phase. So all fields are different, all stories are different, and for that specific question, I don't have a general answer.
Okay. So, any more questions for Alexey? Alexandra Kazanenková. One more. Can you speak up, Alexandra? Oh, here it is in written. Did all petroleum provinces go through primary microbial gas stage? What do you think?
No, that's a good question. Yes, I would think so, right? Because think about the requirements for primary microbial gas generation, right? So you have to have some TOC, you have to have microbes, you have to have low temperature, right? So all sediments do go through that, right? Now the question is why in some basins we have more of that primary microbial gas, and in some basins we have less of that primary microbial gas, right? So, and that's a question about the control on primary microbial gas. So I would encourage you to think in two different directions. So when you drill a dry hole, right, and I don't know about you guys, but dry holes are very useful for me. I learn a lot from them. So when you drill a dry hole, right, you have gas in your well all the way, as soon as you start taking your isotube samples, there is gas, right, and there is a primary microbial gas, and it's in every well, in every basin, right? There's no such well that doesn't have some gas in the pore space, and if you look at isotopes, that gas is primary microbial, right? So we have direct evidence that all basins go through that, right? And when you drill a very deep dry hole, right, you actually see natural transition between microbial gas and then early mature thermogenic gas and then thermogenic gas without any source rock influence, right? Because you have this dispersed organic matter in the sedimentary section that actually generates some amount of gas sufficient for you to see in isotopes, but in isotubes, but not sufficient to generate accumulations, right? So I think the answer is yes, and we have evidence of that. The question is why in some accumulations we have more, in some basins we have more primary microbial gas. For me, two key things are interbedded shale and sand system, right? So the more of that you have, right, kind of thin shale, thin sand, thin shale, thin sand, that system becomes very efficient, right? Because microbes probably eat most of that organic matter in shales, and then that gas can quickly escape into the nearby sands, right? It doesn't have to go through a fixed section of shale. So that's one key thing for me. And also large fetch areas, right? So when you have that system at the right time, forming significant structures to actually focus that gas somewhere to come out of solution, right, and then migrate somewhere, then when it works in big way, and thinking back of accumulations offshore Israel, right, when you have this myosin, sand shale deposition environment. So that's a good setting. So short answer is yes, in all basins, but all basins are different, and in some of them we see it in commercial ways, so in big ways, and in most of them it's just gas in the pore space that we see in isotubes, but we don't see in accumulations.
Mm-hmm. Mm-hmm. Yeah, thank you, Alexei. And are there any questions from the audience? As I was looking in these at these revised diagrams, and I saw, the contrast between the original diagrams that separated the different fields very clearly, and then the revised ones with so much of overlap, it just resonated with the discussion we had just before the start of this on the uncertainty in exploration. So here is another example of just how much uncertainty was underestimated in these original diagrams, and that there is just usually significantly more than what we consider.
Yeah, no, that's true, and so that's one of the directions that I want to go with this work is actually to start putting some kind of confidence levels on interpretations, right? So, and I want to go with a machine learning approach and see how well the machines can actually, given our algorithms, can distinguish between different gases and automatically assign the origins. But with these algorithms, we actually can ask, the computer or the machine to give some confidence levels to interpretations, right? So maybe we'll end up something like this gas, for that given composition is, 80% probability that it's, primary microbial, but maybe it's, 10% that it's actually early mature thermogenic, or, and 5% that it's secondary microbial, for example, right? Mm-hmm. So I don't know what it means yet and how much value we're actually going to get from that. But if this interpretation is very quick, right, and automated, right, then maybe we can actually do something with it. So that's kind of where we're thinking currently. And I have a student who is doing that project. So if anybody in the audience, works for industry and wants to support us with that project, that would be very much welcome.